What we want to do in abstract algebra when we talk about vector spaces is take the definition of a vector space that you learn in linear algebra and make it a bit more abstract. Here's the definition of a vector space in linear algebra. A vector space is a non-empty set V. V is the thing that's the vector space. It's non-empty of objects called vectors. Does that mean the vectors have to be arrows as you always draw them in linear algebra and multivariable calculus? They could be, but not necessarily. They could be, in fact, example of vector spaces includes vector spaces of polynomials. And you maybe remember that from linear algebra. There are two operations, addition and multiplication by scalars, or scalar multiplication for short. The scalars in linear algebra are real numbers. Here's one big way we generalize this in abstract algebra. Instead of saying the scalars are real numbers, we allow the scalars to be elements from any field. The real numbers do form a field, but we allow the scalars to be from any field. And then you've got these rules, these axioms, the first 5 of which indicate that V is an abelian group under addition. So let's start to write this down here. In abstract algebra, a vector space V over a field F is something new. A vector space over a field F is the new way we describe what a vector space is, where F is an arbitrary field in the abstract. It can be any field. You could call it a field of scalars, and the multiplication is going to be a scalar multiplication. A vector space over a field F is, well, let's be as brief as we can here, an abelian group under addition. So there is an addition operation that is a binary operation from V to itself. More officially, it's a mapping from the Cartesian product of V with itself to V itself. That's notation indicating that you take an ordered pair of, in this case, these things called vectors V and W, and map it to V plus W. That's the kind of extra official way to represent the binary operation. We don't typically do that, but you want to be real official about it. So it's an abelian group under addition. Under this operation, it's closed and it's commutative. So it's an abelian group. Associative property, there's a zero element that is the additive identity, and every element has an additive inverse. And then it's tempting to say with these other properties that, oh, it's a ring also, there's a multiplication. But no, that's not quite right. Because when you look at property 6, the scalar multiple of U by C, denoted C times U, is in V. C is not an element of V. It's a scalar, it's an element of the real numbers in linear algebra, or the field here in abstract algebra. So let's just phrase that something like this. It's an abelian group under addition, and there is a scalar multiplication, or multiplication by scalars. Should I use a time symbol for the scalar multiplication? You could. It can be a little confusing if you do sometimes, though, especially in a linear algebra course, because when you put a dot, people could think it means dot product, as in linear algebra. I'm not going to put a symbol for it, but let's specify what kind of operation it is. It's not this kind of operation. It's not something from the Cartesian product of V with itself to V itself. It's something from the Cartesian product of F with V to V itself. Mapping an arbitrary ordered pair A comma V, where A is an element of F and V is an element of capital V, to an element of capital V, A times V. Or if we were using the notation in this book, we'd use a C and a U instead. And there is a scalar multiplication that satisfies what properties? Two distributive properties, an associative property, and a multiplication by one property. And that one there that you see does exist. You don't have to worry about whether there is a unity or not. The field F is a field. Fields always have a unity. They always have a one by definition. If you take that field element 1 times an arbitrary vector, you get that arbitrary vector back. We want that property to hold, and we take that as part of the definition. So here I could say it's for short here with two distributive properties. I'll be more specific about those in a minute here. An associative property and a multiplicative identity property. Okay, so I'm using words here and not being precise about what I mean. What are the two distributive properties? The two distributive properties are the fact that, well, let's look at them here. Scalar multiplication distributes over vector addition. C times U plus V, and I'm going to go ahead and use vector symbols here right now to indicate that those are vectors. I could have used them up here as well. Maybe I should have. The book doesn't do this. Our abstract algebra book doesn't do this, but little half arrow symbols to indicate vectors to clarify what's a vector and what's a scalar is the idea there. So you can multiply, when you add two vectors and you multiply that sum by a scalar, you can distribute the scalar through. Like that. The other property is if you've got the sum of two scalars being multiplied by one vector, you can distribute the vector through, so to speak. Like this. Those are different properties. This is important. This addition here is vector addition. That's the group operation in the vector field, the vector addition. C times that sum, C times that vector is the scalar multiplication. And we're saying you get the same result. Here we're adding the vectors first, then multiplying by the scalar. You can multiply by the scalars first times each vector, then add the results. Here it's something different. C and D are our scalars, they're in the field. C plus D is the field sum operation. That's scalar times a vector. You get the same result here when you add the scalars first before multiplying by the vector. You could also multiply by the scalar times the vector first and then add the vectors. These two additions are different kinds of additions. That's an addition of field elements. This is an addition of vectors in the vector space. Subtle but important points to realize so you don't get confused. That's the main thing you want to, when I say these are subtle but important points to realize, it's so you don't get confused. So you really understand what's going on. The associative property is with respect to the scalar multiplication. This one here, doesn't matter where you put the parentheses here. C times du is CD times U. You can put the parentheses either spot. And it's subtle here once again. When you look at D times U, that's a scalar times a vector, giving you a vector. Then C times that vector is another vector. The result is a vector here. You're doing that scalar multiplication of a vector first time, and then this scalar multiplication of the resulting vector. Here, you're doing multiplication in the field first. C times D is the field multiplication before you multiply by the vector, but you're saying in the definition that you get the same thing if you do it either way. And then multiplication by the identity is this property again. And that is the identity of the field. Why do we make abstract definitions like this? Because we see lots of examples where they hold. That's why. That's what abstract math is about, is unifying lots of different examples. There are lots and lots, infinitely many, in fact, examples of vector spaces out there. We'd like to unify them in one theory, both for conceptual coherence, also for efficiency of proof. You know, if you can prove something in the abstract, then you proved it for those infinitely many examples. You don't have to do infinitely many proofs. That's a big benefit. So conceptual coherence, you're unifying things. You are proving lots of things all at once, efficiency's sake. It's also, I would say, clarifying. When you understand the true reason for something at the most abstract level, that is the core reason why it's true. All the fluff goes away. There are lots of good reasons to be abstract in math, even though it's difficult. Anyway, again, the new thing here is that it's over a field F. The field could be the real numbers. That's what it always was in linear algebra, or maybe once in a while the complex numbers. Or it could be any field. F could be a two-element field, 0, 1, Z2. It could be Z2. Okay? Do you remember the most important things in linear algebra about the theory of vector spaces? Maybe you have no memory of that. I'll say some words. Spanning, linear in, finish it for me. Linear independence. Are those vectors linearly independent or not? Oh, nightmares. Basis, oh, the worst nightmare. Basis. Change a basis matrix. Dimension. Oh, that's a big one for us. Dimension. All those ideas about spanning, linear independence, basis, dimension are what you find in the old chapter 19. And they are the most important things for us, actually. Yes, there's examples, but let's look at the abstract definitions here. Let's first think about spanning. It's in the context of an example, actually, though it could have been a definition. Let V be a vector space over F. Okay, you got your bearings. V is a vector space. It's over a field. Elements of that are the vectors. Elements of this are the scalars. We're not going to bother with vector notation in this book because it can be made clear by using words or symbols. Those are vectors. These are not necessarily distinct elements of V. Oh, this kind of notation looks familiar. What was this in ring theory? That was the ideal generated by V1 through Vn, but this is vector space theory. Vector spaces are not rings in general. So this must mean something different, but it is an analogous kind of thing, if you recall. From back in chapter 13, I think this was defined to be the set of all ring linear combinations of the elements that were in here. It's a similar idea. All linear combinations of the vectors where the coefficients are from the field in this case. You do think of the vector space and the field as being different objects. Maybe the vector space is over here and the field is over here. Or since we're calling it a vector space over a field, maybe you put the vector space up here and the field down here. Do we have to do that? It's kind of weird terminology to say it's a vector space over a field. And no, you don't have to visualize it like that. The vector space doesn't have to be visualized up here and the field down here. It's just terminology. But they are separate things. They are separate sets. The A's and the V's are from separate sets. But when we form this linear combination of them, it's in V, not F. A scalar times a vector is a vector. Those are all vectors. A1 times V1 is a vector. A2 times V2 is a vector. I'm adding those. That's in the vector space. Vector space has a vector addition. This is called the subspace of V spanned by the V1s through Vn. And in linear algebra, you use different notation. You use the word span. You remember that? Span V1 through Vn. This is the same idea. except the A's are from an arbitrary field, whatever the field you happen to be thinking about. By the way, V, the vector space, could be a vector space over different fields as well. The field does matter, but there could be different fields over which it's a vector space. Weird, but true. Any sum of that form is, like I said, verbally called linear combination of the V's. If the span of V1 through Vn is equal to the vector space, we say that that set spans V. This is all linear algebra, except now the scalars are from an arbitrary field. They're not necessarily real numbers. They could be rational numbers. Q is a field. They could be complex numbers. C is a field. Like I mentioned a few minutes ago, they could be just 0 and 1. Z2 is a field. Or 0, 1, and 2. Z3 is a field. ZP is a field when P is prime. That could be from ZP. This definition. A set S of vectors is said to be linearly dependent over a field if when you take those vectors from S, some of them at least, there are elements A1 through AN from the field, not all 0. That is not a throwaway phrase. Not all 0, such that the linear combination of them gives you the 0 vector. And a set of vectors that is not linearly dependent over the field is called linearly independent over the field. Just a little different, I think, than the definition in linear algebra. In linear algebra, you usually define linear independence first, and then you say linear dependence is not linear independence. Here you're defining linear dependence first, and you say linear independence is not linear dependence. That gets confusing. What'd you do in linear algebra to define linear independence? V1 through Vn is a linearly independent set. We'll add the phrase over a field over F now. If what? If when you had an equation like this, where this linear combination equaled the 0 vector, that implied all the A's are 0. That was enough to imply all the A's were 0. That was your definition of linear independence in linear algebra, though in that class, the A's were taken to be real numbers. And then you said linear dependence, a set of vectors was linearly dependent if this is not true. Meaning, there are some non-zero scalars for the A's that make this linear combination equal to the 0 vector. Which is exactly the definition the book here gives for linear dependence. There are some non-zero A's making this 0. Okay, so these are equivalent to each other. Again, the new thing is the A's are from an arbitrary field. And this is important for what comes next. And then we have a definition of a basis. Yeah, nightmares. Let V be a vector space over F. A subset B of V is called a basis for V if two conditions hold. V is a linearly independent set over F, linear independence, and it spans V. Every element of V is a linear combination of elements of B. And what did you see in linear algebra as far as examples went? You know, things like R3, three-dimensional space, three-dimensional vectors, the set of all, well, you wrote them as column vectors in linear algebra. A1, A2, A3 as AI varies over R, where you add column vectors component-wise and multiply them by scalars component-wise. The standard basis is your favorite basis. B equals 1, 0, 0, 0, 1, 0, and 0, 0, 1. Also called, well, I hat, J hat, and K hat in physics. And in linear algebra, sometimes you call them E1, E2, and E3. Not the number E. But you also saw in linear algebra that there's lots of other bases for R3. In fact, any three vectors that are linearly independent would automatically be a basis for R3. And I don't know if Al emphasizes this, but whenever I teach linear algebra, I emphasize that if you write down, let's call the basis C, if you write down three random vectors, oh, I don't know, 2, -7, 3, -1, 0, 4, 17 pi. Okay, if I put a pi in there for sure, this will work. 17 pi 9, three somewhat random vectors. In all likelihood, maybe especially because of the pi in there, this will be a linearly independent set, and therefore will be a basis for R3. But why? Wait, why does being linearly independent means it spans? Why? Because there's a theorem about that. That's why. R3 is three-dimensional. Dimension of R3 is 3, and not just because there's a 3 up there, but for another reason I'll get to in a minute. So there's also a theorem in linear algebra, I believe, called the basis theorem, that says if you know the dimension of the vector space, in this case 3, any three linearly independent vectors in that case in R3 is going to form a basis for R3. It'll automatically span. And likewise, if you've got any three vectors that span, it'll automatically be linearly independent. But why is the dimension of R3 3? Is it really just because there's a 3 there or not? Well, I mean, it's related to the fact that there's a 3 there, but the official definition of dimension is the number of elements in any basis. The dimension of the vector space is the number of elements in any basis. But that should bring up a question in your mind. Like, well, how do I know that any basis has the same number of elements? That's a theorem. It's a theorem in this old chapter 19, right here. Invariance of basis size. If you got two bases of the same vector space over the same field, one with possibly call it m vectors and one with n, where m and n a priori could be different. Well, guess what? They're not different. They're the same. That's the conclusion. So if a vector space has a finite basis, any other basis will have the same number of elements. And that number of elements is called the dimension. Though I should say there are vector spaces that don't have a finite basis. They're not spanned by finitely many elements, for example. Can I think of an example? Sure. Example I always bring up in linear algebra is this one, but there are other examples. That's a C, cursive C. What's that? Get this. This is the space of all real valued continuous functions on the closed interval from A to B. What did I just say? You heard me. Listen carefully. It's the space of all real valued continuous functions on the closed interval from A to B. An element of this vector space is a function, a continuous function. Any continuous function on this closed interval whose outputs are real numbers, real valued. You will find this example in your linear algebra book. It's there. Look in chapter 4. It's an infinite dimensional vector space. Doesn't have a finite basis. There's no finite collection of continuous functions you can come up with that spans this, meaning every function in here is a linear combination of those finite number of functions. Can't happen. And if you think about it intuitively, it should make good sense, because like what's in here? Well, every polynomial's in there for one thing. Every trig function, that's a linear combination of cosine and sine. I'm avoiding tangent and cotangent and secant and cosecant because those have vertical asymptotes. E to the x is in there. Any exponential function, e to the negative x. Ln of x, if a and b are positive at least, is in there. And plenty of other functions that don't even have names. Maybe you just draw their graphs, they don't have formulas. There's infinitely many functions in there, but that's not the reason it's infinite dimensional. It's because there's no finite collection of functions you can create in such a way that every continuous function is a linear combination of that finite set. Not possible. So there are vector spaces that have infinite dimension.